This video will be on magnetism. So anything containing iron can become magnetized. We can put it next to a magnet and it will act like it's magnetic. We can force things with iron in them to line up. The atoms kind of line up in these domains and they will act like they're magnetic. We call those ferromagnetic metals, ferro just meaning iron. And then as you guys know from, I think, kindergarten and on, when you have two magnets, they can either attract or repel each other depending on which way they are situated. All right, when we look at magnets, there's a north and a south pole. And I'm sure you remember, north to north repels and south to south repels, but north to south attracts. And the terms north and south are just conventions, right? We could have labeled these things just about anything and just said, blue repels blue and it attracts red. But we've done that conventionally, and so we're going to stick with that. So we have north and south poles. Those are going to attract. North to north will repel. South to south will repel. Okay. And I think you guys have seen this before, so we're not going to do this, but you can do this as a lab. You can take some iron shavings and lay them down and put a magnet on it, and you can see the magnetic field. You can actually see the magnetic field. And in this magnetic field, the magnetic field points from south to north. So when you draw it, you want to draw it conventionally north to south, and you can see it's here. And you can kind of see it all will point to the 2 points. It all points here. So these lines kind of all go this way, and then these loop around. You can see they loop around this way, and they'll point also to the South Pole, and these will come out straight. So that is your field right there. You can actually see the magnetic field. All right, so what can we kind of have similar atomic structure, anything around iron? It's the electrons, we can get them to line up and act magnetic. All right, US, we don't have magnetic coins, fortunately. But other countries do use ones with iron in them, and so you can magnetize them. Oddly, just a side note, you don't have to write it down. Sorry, it's not grayed out. The ink in the US dollar actually has some iron in it, but that's for counterfeiting purposes. Okay, so when we talked about like you can line up these things, here's an example. Here's a microscopic view of a crystal, and you can see the arrows are kind of pointing kind of randomly everywhere, and you can just think of a crowd of people that are just walking every which direction. That would show a non-magnetic piece of iron. All right, it's just everything's just not aligned. The arrows are a jumble. Okay, if we line them up like the bottom iron here, you can see is strongly magnetized instead of a crowd of people walking every which way. You can think of them like, a drill team, and they're all going one direction. This also explains exactly why I scream at students and yell when they drop a magnet. It unmagnetizes it slightly over time. You can see here all these nice, arrows point in the same direction. This will act magnetic. You can imagine in the strong magnet, you have arrows pointing the opposite direction, or sorry, excuse me, the same direction here. And it's going to act magnetic. If you drop it over time, you end up with sort of something that looks like this, where they no longer point perfectly the same direction, and it becomes less and less magnetic over time. All right, so if you want to magnetize iron, you can hold it next to a strong metal, and it will act as if it's a magnet. And you can see over here, the idea that what you're looking at over here is here's a nice strong magnet, and this nail, which is near it, is acting like a magnet, and it's actually holding the nail beneath it, right? So it has magnetized this nail, and it will act as if it's magnetic. All right, you can scramble these domains by heating them and then whacking them. You can also just drop them 100 times over and over and over again. That will work as well. Okay, and again here you can, this is just a demo where you show that it's a strong magnet is pulling the nail, but if you heat it, it won't be attracted to it because those domains become randomized again. All right, electric, as we look at magnetism, right, it used to be that electricity and magnetism were thought to be two different things. They were independent of each other. And now we call that electromagnetism, right? We put those together and we have figured out over time that these forces have similarities. You can combine it. It's actually what led Einstein to really push for his grand unified theory, was thinking, well, we could take this force electricity and we could take magnetism and we can combine those to electromagnetism. Maybe we can combine gravity and the strong nuclear force and we could just combine all the forces. And we know that never worked out. But this idea that electricity and magnetism do combine was what historically led that to occur. And you can see if you just take a current through a wire, you create a magnetic field, and it's just showing you here the magnetic field. Just like you saw around a magnet, you get a magnetic field around a wire, and you can use compasses to see that magnetic field. All right. So here we have, again, the exact same thing. We have the magnet on the left side, and we have a current running through a coil. And a coil is going to become important here as we talk about magnetic fields and how to create electricity. We use a coil. But if you take a coil and you run electricity through it, you've created a magnetic field, and you can see it with the iron filings just as well as you could see with a real magnet. All right. When we do, we're not actually going to do this lab, but you have an electric coil, and if you put an iron bar in it, you actually get a better, stronger electromagnet than if you have it without the iron bar in it. But both of these will create a magnetic field. All right, so practical application. A loudspeaker is a great example of practical application. You take some magnets in it, right, and you're going to pass a current through the place where the loudspeaker attaches right there. And as you change that current, you're going to pull or repel the speaker cone, right? And you're compressing the air as you do this. If you push it, you get an area of compressed air, right? Which is, go back to our sound unit, areas of compressed air or where it's been decompressed create your sound. So you're going to take this coil and you're going to take a current through it and you're going to go back and forth. Then you have a magnet sitting there and it's either going to repel or it's going to attract. So you go repel, attract, and you'll create sound that way. That's true all the way down to your little tiny headphones. It's just that they're much, much smaller. All right, the Earth has a magnetic field. Up at the North Pole is the south part of the magnetic field because that's why your compasses point north. They say north, but that's actually the south part of our field. And there is just a large magnetic field around the Earth, which we need to be super, super, super grateful for. It is what takes all of the radiation from the sun and deflects it around of our solar wind from the sun. It deflects it around the Earth. Up at the north and south poles, you can see something called aurora borealis or aurora australis down at the south pole. And that's actually the radiation from the sun, the solar winds, hitting our planet and getting deflected around it. What would happen to our planet if we lost our magnetic field? You need to look at Mars, right? Mars used to have water on it, used to have an atmosphere. That got blown away. Why did it get blown away? It lost its magnetic field in all likelihood. And then the solar winds will just strip the atmosphere off and you'd be toast really, really quickly. So our magnetic field is a beautiful protective thing for us. And it comes probably from the currents on the inside of the Earth. And so we say, well, look at the currents on the inside of the Earth, and you can see, you can kind of imagine the North and South Pole. But what's interesting, and we're spinning so that the North Pole is close to the top of the way we spin. But what's interesting to me is that Uranus actually, its North and South Pole is like at a 60-degree angle compared to the way it spins. It actually rolls around on its axes, and its North and South Pole are significantly off from the way it's spinning. So just kind of an interesting side note there. Okay, we can use magnetic fields to put a force on a current. You can take a current and you can actually bend it, right? Force up or force down as it passes a magnet. We can do that with currents. We can do that actually with electrons as they pass. You can take a magnetic force in a wire, and we can then measure how much current is passing in it. And that's what an amp meter is, basically. You just take the amount of bend that you're getting, and you can tell the force applied, and you use that on a little needle, and it tells you the amount of current that's passing through there. Okay? We can take our forces and we can apply them to electrons as they pass through. We can take an electron beam past a magnet and we can bend it. And that's in a tube, a Crookes tube. You're actually taking the magnet and you're bending the electron beam. Okay. Old TVs used to work, old, way back in like the 80s and 90s. They took TVs, and the way that a TV was is it just deflected this electron beam, and you can see your colors there, the same colors you're very familiar with, and it would deflect them, and you would get the colors on the screen. You could take a magnet and put it near that screen, and you could actually see um, those blue, green, and red beams. You could kind of deflect them out like a rainbow type color. And if you took that magnet, you could see those beams. But, it was bad for your TV.